Have you mentioned questions yet, Diane? That we'd like, if you pop those into the chat line, everyone, we can then consolidate the questions and deal with them when we get to the end.
Perfect. Okay. I think we're good to go, really. Save hanging around too much longer.
All right. Thanks, Diane. Well, I'm Russ, Russ Swinnerton. I'm an ex-Navy navigator. So I trained actually in the UK and Europe in marine navigation, was a navigation specialist, 2 sea commands and a bunch of navigator jobs. I've been paddling for about 12 years, now with the Burley Griffin Canoe Club and the New South Wales Sea Kayak Club. But I'm the theory guy. And as you've seen with our first webinar, we brought Adrian, the practical guy, along. Adrian's overseas. So in his stead tonight, we've got Campbell. Someone, we may need to mute someone who's talking. That seems to have gone quiet again. So in Adrian's stead tonight, we've got Campbell Tiley, experienced expedition paddler, former president of the New South Wales Sea Kayak Club. We've done extensive rehearsals of our to and fro. We haven't. So Campbell will be available to chime in with some practical tips, the way Adrian did in our first webinar. So we'll look for opportunities where he can add practical experience to my theoretical explanations. As we mentioned, please save questions to the end or pop them in the chat line so that we can consolidate them. And I'll start with our slide set now. I'll be breaking periodically to come back to face so that we can catch up. If there is something that's paralyzing you with indecision, then we can deal with that as we go through if there's a consensus. So we'll try to break up the slides with a little bit of side commentary as we work. So here we are with our introduction, the paddle education program with Paddle New South Wales, the auspices under which we're running this series. Tonight, it's maps and charts in terms of our expedition planning for kayak adventures. Diane's already mentioned we are planning a practical on-water day for you, if you'd like to join in with that. Venue to be decided when we see where the participants' centre of gravity is. That will be the 19th of November. Tonight, charts and maps. Next session, webinar 3 on the 11th of October, we'll be dealing with natural phenomena. So that's about winds, tides, currents, swells, all that stuff. And the final webinar on the 8th of November, putting together all the theoretical stuff and talking about navigating from the cockpit, piloting as it's called, how we give effect to our plans to execute a navigational passage. Margie asked that we just remind you, those of you who listened in to webinar 1, what the things to remember from that session were. We'll be building on some of this as we work through the webinar series. So the things we highlighted there was do your detailed planning at home on the kitchen table where it's dry and steady and stable. The more planning you can do there, the easier will be your execution when you get on the water. We talked a lot about magnetism and compasses. Can dead men vote twice was the compass deviation, M for magnetic, V for variation, T for true. And the way we figure out which way to apply our variation errors compass to true, add east, subtract west. On the east coast of New South Wales, our variation is always east, so that's a quick and easy way to remember which way to go. We talked about different compasses for different tasks. We can use a steering compass for steering a course, of course. We can use a hand-bearing compass for taking bearings of objects, and we can use a bushwalking compass to do all of those things. Very useful piece of kit. It also works as a protractor on our spray deck. Bushwalking compasses are now available with a prism, so you can get the same kind of accuracy taking a bearing that you can with a hand-bearing compass. We talked about being able to measure your distance off by the height or width of a known object, and we can use our fingers or a centimetre rule on a 57.3 centimetre piece of string to be able to measure degrees. We spent a really productive second half of the session talking about electronic aids, GPS and communication devices. So you're reminded that GPS is only as good as the accuracy of the waypoints you enter, but it's a great thing. Don't rely on it. Remember, batteries can fail. You can lose the thing over the side when the lanyard fails. So we're talking about traditional navigational techniques that will support you when your GPS drops out. But we had a really good chat about communications using some of the modern devices that are out there. Spot and InReach giving you satellite messaging, really handy, on top of the utility of a mobile phone when you're in range, or marine VHF, same line of sight pretty much. So tonight's session, maps and charts. We're going to talk a little about the nature of the globe on which we reside and how we define position on the globe with latitude and longitude. Once we move from a spherical globe to a two-dimensional paper representation, we're going to have to make compromises, and we'll talk about what those compromises are. We'll introduce topographic maps, and talk about why they're different to marine charts. The big difference with them is contour line, details about the land, but particularly the shape of the land with contours. We'll talk about scale and distance on both maps and charts. We'll talk about datums. So that's datums both in terms of horizontal datums, connecting your map or chart to that oblate spheroid that is the globe, and also vertical datums, how a chart has a chart datum that allows its depths to be expressed below that datum. So datums and direction we'll cover. A little about maritime chart symbols, but mainly the ones that affect us in terms of our safety on the water. Dangers, tidal streams, eddies and overfalls, that kind of thing. And finally, we've got a couple of exercises on reading map contour lines, deciding what the Earth looks like based on the representation on our topo map. So mainly tonight, we're going to be talking topos and marine charts, but that's not all that's available for us when we're planning an expedition trip. Don't forget, New South Wales boating maps are a really valuable source of information. They're cheap, they're waterproof, they're not to be used for navigation, of course, but they're a really handy thing to have under your bungees. Fishing maps will give you a lot of valuable information, so will tourist maps. And don't forget Captain Google at your service day and night. You can find a lot of useful stuff on the internet if you're a discerning customer. Okay, so let's start. Now, this is kind of background knowledge that you did in primary school, but we're just going to run through the basics of latitude and longitude, shape of the Earth, to make sure we've got a baseline understanding that connects with that stuff. So on the sphere, we use a system of coordinates that we call latitude and longitude. So parallels of latitude are parallel circles that are centered on the axis of rotation of the Earth. The largest one is in the center of the Earth, it's the equator, and they are then measured in degrees from the equator, from the center of the Earth to the poles, and the poles are at 90 degrees. So nothing new there. So think of it this way, that protractor is centered on the center of the Earth. The North Pole is at 90 degrees, the equator is at 0, and that equator line runs all the way around the Earth. Longitude is different. So meridians of longitude are run from pole to pole, okay, and they are based on a prime meridian, which is defined as our 0 degrees of longitude. And then our meridians are measured in degrees east and west of the prime meridian. So 180 east and 180 west is the same line. It's the same meridian. The prime meridian we use today is the line that runs through the Greenwich Observatory in the UK, and that's accepted internationally. So any position on the surface of the Earth can be described in terms of its latitude and longitude. So we've got a couple of spots on the diagram there on the slide, 40 degrees north, 32 degrees west, and 40 degrees south, 32 degrees east. That gives you a sense of it. So whenever we're describing a position in terms of latitude and longitude, we quote the latitude first, so north or south, and our longitude, east or west, second. So our degrees of latitude will run from 0 to 90, our longitude from 0 to 180. You'll see I've put the end of that slide. I'm using minutes and decimal minutes of degrees, and we'll talk about that a little more in a moment. But that's the way it would be expressed. And they're the shorthand symbols we use. A degree symbol for our degrees, a minute symbol, single dash for minutes, and seconds we use the double dash. Just a couple of fun facts for you. There's an underpinning celestial navigation reason for the decisions we've made with our latitude and longitude systems. Once upon a time, longitude was just measured west from 0 to 360 from the prime meridian, because that made our calculations in celestial navigation easier. So that's the apparent movement of the sun and the moon and the planets and the stars, is from east to west. Now, for convenience, we start at the prime and go east and west. In an hour, the sun will traverse 15 degrees of longitude. So in 24 hours, it'll appear to pass over the whole 360 degrees. We have lines called the tropics, and that's as far as the sun reaches in terms of passing overhead during the year. So the sun is overhead at the solstices at 23.5 degrees north and south, and at the equinox, it's overhead the equator. And until 1884, countries could set their own prime meridians. There's a little interesting fact for you. So Alexandria, Copenhagen, Madrid, Paris, St. Petersburg, Washington, and Philadelphia, apparently, have all been prime meridians. In 1884, the maritime world settled on Greenwich as our 0 degrees. So we had a commonality of latitude and longitude. Now, by convention, we divide our degrees of latitude and longitude into 60 minutes and 60 seconds. So each degree into 60 minutes, each minute into 60 seconds. But in navigation, we tend to use decimal minutes rather than seconds, again, for convenience. That's about the level of accuracy we're interested in. 1 minute of latitude measured on a meridian we take as a nautical mile. And I'm going to talk a little more about what that actually means in terms of distance in a moment. Again, an interesting factoid, we call 1/10 of a nautical mile a cable in nautical terminology. So 10 cables to a mile. And meridians and the equator are great circles. So by great circle, we mean as large a circle as it's possible to draw on the surface of the Earth. And 1 minute of arc on a great circle is a nautical mile. So that's the theoretical basis for this. When we move from a 3D globe to a 2-dimensional chart, we've got to make some compromises. So if only we could navigate on a globe. And in fact, with GPS, that is what we do. We have the WGS-84 globe as a system in our GPS. So the coordinates it's giving us are based on a globe. But we have to represent our maps and charts on 2-dimensional paper. So we're making compromises. And there's a nice saying there that all models are bad, but some models are useful. Our projections are models of the Earth's surface, represented on a flat plane surface. So there is no perfect 2-dimensional map. We're making compromises everywhere we go. So how do we locate our 2-dimensional map on a 3-dimensional globe? So we need a horizontal datum that connects to it. So WGS-84 is what marine charts are based on. So the latitudes and longitudes displayed on the marine chart connect to that globe using the WGS-84 datum. Okay, so all our marine work, all our stuff at sea, WGS-84, put that in your GPS. Land mapping, so the topo charts, sorry, the topo maps we use to give us information about the foreshore or to be used when we're planning pullouts, communications, that kind of thing. They're based on the geocentric datum of Australia. So Australian land mapping uses, now it uses GDA 2020 or just GDA, so the geocentric datum of Australia. And differences between those two, GDA 94 and GDA 2020, are less than 2 meters. And differences from WGS 84 are trivial. So you can transfer a position to a paper map using WGS 84 and you'll be accurate. Unless your topo was drawn to a different earlier datum. So you've got to check your paper. Check what datum it uses. So GDA 2020 is compatible with WGS 84, and the differences from the earlier GDA 94 are also trivial. But if your map was drawn to the Australian geodetic datum 66, then your positions could be in error by up to 200 meters. Okay, so please check. I might just pause there, and we're about to talk about Mercator projections and get into some more of the nuance of the compromises we're making with paper charts. But I'd like to just pause there for a moment and see if Campbell has got anything he'd like to chime in on the problems of comments to give me time to have a glass of water.
I'll try, Russ. The microphone's getting a lot of feedback. I'm not sure what's happening here.
We can hear you okay.
Oh, okay. Okay. No, well, I was worried I'd be expected to come up with intelligent Adrian style chip-ins, which is obviously a big ask. But I must admit, I'd really just reinforce that the datum stuff sounds incredibly arcane and the sort of thing that an ancient Navy mariner would go on about. But that, as you say, it can actually trip you up. And I haven't had that experience, but I have heard of cases where people have been using old maps and just haven't been able to work out why it doesn't G with their GPS. And it is worth checking that you've got the right setting in it once.
So here is a topo in my hand, and all of the information, as we'll say in a moment, is on the back of the topo. It tells you all about it. This is drawn to GDA 96, so not the latest datum, so it's a few years old. But it does make the point that differences to WGS 84 position are trivial, a meter or two. It does say, though, that height, using the GDA 96, heights on your topo could be different to a WGS 84 height by up to 20 meters, which is quite significant if you're climbing mountains and things, or carrying your portage in your kayak over a hill in between one beach with a crocodile on it and one beach without a crocodile. Those 20 meters could make a difference. So the map tells you all that stuff. It'll tell you on the back how you're doing for comparing with WGS 84. But for a marine navigator, that's what you want on your GPS. So let's talk about Mercator projections now. Again, this is primary school stuff. You will have learned about this. I'm just refreshing us, giving us a baseline. So down the bottom of my slide there, you'll see how we visualize a Mercator projection. We wrap a cylinder of paper around a globe, and we project from the center of the globe out to the paper surrounding it. So a Mercator projection gives us vertical meridians that cut through our parallels of latitude at 90 degrees. Now, as you think about that, that's fine down near the equator, but as you move further away from the equator towards the poles, you're getting distortion in those squares of latitude and longitude. The further from the pole, the further from the equator, the greater the distortion. The advantage of this projection, so that's the compromise you're making, you're getting distortion. On a large scale map covering a small area of the surface of the Earth, that distortion is not going to worry you very much. And the advantage of this projection is that you can plot courses and bearings, cutting the meridians at the same angle wherever you are on the map or chart. So that's a real plus. You can take a bearing, you can lay it off on a Mercator projection, and that line is a straight line. Now, I mentioned scale there. The convention for referring to scale is that a small scale map or chart covers a large area of the surface of the Earth. Last webinar, we recommended you buy Ferrero's book on sea kayak navigation. He muddles these in his book and gets it the wrong way around. But this is the definitive definition. So small scale, big area. So we see a lot of the ground, we don't see a lot of detail. So small scale maps are little about a lot. Large scale maps, we see a lot about a little. So a large scale map covers a small part of the Earth's surface, but in much greater detail. So when we're deciding what scale to use, we have to think about the difficulty of our paddling task. If we're in an area we know well, we can get away with a reasonably small scale map or chart. But if we don't know the area, or if it's complex, then we need a large scale. So professional mariners who are steaming around our oceans will have a small scale chart to cross an ocean, getting progressively larger as the land they can see increases. until they're on a 1 in 25,000 maybe, or smaller, sorry, or larger, smaller representation as they enter harbour. So depending on your task, you settle on your scale. 1 in 50,000, so 20 millimetres on the chart equals a kilometre, is what we reckon is a good standard scale for complex navigational problems. But poor old Stuart Truman would have needed 500 of those to get around Australia in his circumnavigation. So there's a budget consideration in terms of the cost of getting this stuff, the weight, if you're going to have paper charts, and the space that you're going to need to carry the number of charts you'll need to cover the area you're traveling in. Flying in aeroplanes, in the good old days, we used to have to carry paper maps for all of the areas we'd be covering and any likely diversions. So you ended up with a bag that weighed about 20 kilos of paper maps. The Civil Aviation Safety Authority now permits us to use an iPad for flying as an electronic flight bag, it's called, and that is your authority. You don't have to carry paper. The advantage of an aeroplane is that it runs out of fuel periodically and has to stop on the land so you can recharge your iPad. It's a different story at sea. So as we covered last webinar, electronic maps and charts, unless they're the authorised version provided by the hydrographer, are not authorised for navigation. That is obviously one of the solutions to this space problem if you've got your charts electronically. The advice was use those by all means, but check against an authorised navigation chart before you head off on a difficult passage in an unknown area. So back to this question of distance on our chart. So nautical mile, 1 minute of latitude measured on meridian, that's easy. The trouble is, because the Earth isn't regular, so it's an oblate spheroid, that is, it's a squashed globe. So a minute of latitude towards the poles is different to a minute of latitude near the equator. And you can see the range there on the slide. Around 1861 metres near the poles, 1843 at the equator. Over the years, we accepted that a minute at 45 degrees, so halfway between pole and equator, would be our standard. And we've since adopted that as the International Nautical Mile. That is 1,852 metres exactly. And that's what we use for measuring distances, for calculating our speed across the water, that International Nautical Mile. For celestial navigation, we still use the minute of arc, wherever we are, whatever our altitude, measured off the chart. But for terrestrial navigation, we're going to use International Nautical Mile. You may prefer to use kilometres per hour. That's fine, but if you do, you're going to have to do some conversions from time to time. Okay, now, here's some mental arithmetic tricks for you when you're doing the conversion. A lot of people, they hear a wind strength in knots, they want to convert that to kilometres, they'll just double it. Converting kilometres to nautical miles, they'll often just halve it. But you'll get a more accurate estimate. So none of us wants to whip out a calculator and divide by 1.852. If we divide by 2 and add 10%, okay, we get a near enough estimate of the number of nautical miles that are equivalent to our kilometres. So we want to know how many nautical miles is 36 kilometres. Divide by 2 is 18. Add 10%, 1.8, we get 19.8 nautical miles. The exact answer when we work it out is 19.44. So that divide by 2 at 10%, It's easy mental arithmetic, and it gives you a near enough answer. Moving the other way from nautical miles to kilometres, similar rule applied the other way around. Multiply by 2 and subtract 10%, and we get again a close approximation. So how many kilometres in 10 nautical miles? Now we can actually do that one pretty easy, multiplying 1.852 by 10, but using the mental arithmetic formula, multiply by 2, we get 20, subtract 10%, we take off 2, we're left with 18. So the exact answer, 18.5. Okay, so we'll be talking a lot more mental arithmetic tips in the 4th webinar when we're talking about how we keep track of our position when we're on the water. What are some of the tricks we can use for quick answers when we need them? But there's one. You're going to work in kilometres per hour. Recognise that you will need to be converting from one direction to the other sooner or later. I work in knots on the water, unless I'm in, for some reason, unless I'm in fresh water, where I tend to use kilometres per hour. But I've grown up with knots, and it's natural for me to think that way. If you're paddling, kilometres sounds better because there's more of them for your hourly transit. But knots, when you're on marine charts, knots are what I use when I'm in freshwater. I've normally got a topo app. If I'm paddling on a river, and that's in kilometres, so kilometre per hour works just as well. As long as you're comfortable with the conversion, there's no drama. So talking charts now, we're talking direction. So charts and maps take direction differently. And we'll talk a little more about that in a moment, about how topo maps do it. But remember, with a Mercator projection marine chart, the meridians are vertical lines and the parallels of latitude are horizontal lines. They cut at right angles. So our marine chart is going to have one or more compass roses, that's what they're called, printed on the chart to give you direction that applies right across the chart. So compass rose 360 degrees with the magnetic variation for that location shown on the compass rose. In the good old days, we seafarers used to have a custom is probably too strong a word, a habit of dividing the 360 degrees into 32 compass points. And that was how we used to describe wind and sometimes courses. So we would box the compass to show how well we understood the principle of those 32 11¼ degree points. So that was north, north by east, northeast, northeast by north, northeast, and so on. Not used much anymore, thank goodness, except for things like the arc of visibility of a ship's navigation lights. So they show in an arc from right ahead to 2 points above the beam. That is 22½ degrees behind the beam. So the point system still gets a run now and again in some of those traditional measures. But the arcs and navigation lights have been set that way since the days of sail, so hence they're still using points for that. The rest of us, 0 to 360. That means we can use plotters anywhere on our marine chart. We no longer have to use a rolling rule to move bearings from the compass rose to where we want to draw a line. So plotters are much more convenient. We talked about that in the last webinar. Forget rolling rules, even on the kitchen table. A plotter that has grid lines that you can orient with the north, south, east, west lines on your chart, much more useful. And just a small point here, when you get into the business of starting to use courses and bearings and calling them out across the water, try to make your courses and bearings 3 digits. So even if the first digit is a 0, include that in your course. It's just easier to hear when the wind's blowing and the water's washing over your boat if you're hearing the expected number of digits. So 025 is a bearing of 025 degrees, not 25. Now, just a couple of other sort of fun facts for you. A straight rumline course on a Mercator projection is not the shortest distance between 2 points. I mean, it looks like it should be. It's a straight line. But remember the distortion that's inherent in a Mercator projection. Okay, so the shortest distance on the surface of the Earth is actually a segment of a great circle. So when we represent a great circle on a Mercator projection, it actually looks like a curved line that bends towards the pole. And if we're actually doing an ocean passage like the east coast of New South Wales to New Zealand, for example, we could well use the ocean passage trick of steering a series of straight lines to approximate the great circle route. Okay, on a Mercator chart, it's going to look like a curved line, but it's actually shorter than that rum line, that constant bearing across the meridians. Okay, so we've been talking about marine charts there, direction, distance, scale, that kind of thing. Now we're going to talk a little more about topos. And I'll warn Campbell that I'll invite him in a little while to talk about how he sees the benefit of one versus the other. So the big difference with topos is that they show detail on the land. A marine chart only gives you enough to be of use to a cruising mariner. So you're just seeing peaks, ridge lines, indication that there is a population centre somewhere, but you're not getting that real granular detail that you see on a topo. So marine charts have some contour information, but it's much more sparing. They'll sometimes use shading as well to indicate the shape of the land, but topos will have regular contours at a fairly close interval, so you get a much better sense of the shape. Topos use a different projection to marine charts. So topos use a global system. It's a universal transverse Mercator projection system. So the way to imagine that is to think about our cylinder of rolled up paper held horizontally around the globe, not vertically, the way we do for a standard marine projection. So transverse Mercator, it's tipped on its side. The meridians are no longer parallel lines. Okay, that's the big secret. So instead of latitude and longitude, a topo map uses a grid system based on that universal transverse Mercator projection system. The grid squares are kilometre by a kilometre. Okay, 1 kilometre square. It's similar to latitude and longitude, but it's not the same. There will be a lat-long reference on your map to show you where that map is located, but the grid system of eastings and northings, each of those squares covers the same amount of real estate, 1 kilometre by 1 kilometre. And not like the latitude and longitude squares we see on a marine chart. Okay, so that diagram on the right is a kind of exaggerated shape of a UTM projection, universal transverse Mercator. So the grid squares are overlaid over those meridians that are represented as curved lines. So north, direction on a map comes from grid north, not from the meridian. Okay, now your map will tell you what the difference is. At the center of the map, it'll have a thing like on the bottom of that slide showing you the difference between grid north and true north, and the difference between both of those and magnetic north. So magnetic north is what your compass is going to be giving you. Grid north is what your orientation of your map will be. And the difference, the map will tell you in its north points diagram what that difference is. Okay, so that's one of the main differences in terms of using topos and marine charts when we're reading off a direction. Let's just pause there. One of the things we're going to talk about now is, or shortly, is what we use when. So when is a topo useful for us and when is a marine chart useful? And I've got a couple of comparisons to come. Before that, we've got a little more nuts and bolts to do on the topo, but I thought now that we've warned Campbell that we're going to invite him to say something, your experience of the two, are you a marine chart person or do you use topos a lot?
Well, I'll have to make sure I sound intelligent, having been warned. I mean, I think it depends very much where you're traveling, but given that most of the places we'd be I would be paddling would either be very close to the coast or up inlets, they're both incredibly useful. And certainly for a number of the longer trips I've done, I would, you know, have both on deck with the topo laminated on the back of the chart. And I mean, obviously on the water, there are a whole lot of things on the chart that are really useful to be warned about. And I mean, you've, I think, mentioned earlier about things like overfalls and bommies and just, you know, general hazards of the shoreline. On the other hand, there are some very obvious things on topos which are incredibly useful. Certainly, if you're looking, to be aware of places for emergency putouts, roads, access, that sort of thing. The topos are great. Finding campsites and you know, finding a good sheltered spot to camp. Topos are great. I guess the details of the shoreline, how comfortable it's going to be for kayaks, the charts better for that. Obviously all the information about current flow and tides, there's often quite a bit on the chart that you can just glance at. So I think they're both incredibly useful. I mean, aids to navigation on a chart are actually quite useful for handrailing type navigation quite often, particularly going up an inlet. So they'd be the things that immediately spring to mind.
Yeah, we talked about this briefly in webinar 1, laminating an extract of a chart or a map, and as Campbell says, having both available is the way to go. That's the luxe solution if you've got access to the resources. So you can often get a marine chart electronic system that will give you the ability to print extracts, print those out, laminate them with topo on the other side, and you're in business. You've got the best of both worlds. Great, thank you. So let me just now talk a little more about eastings and northings. Again, you will have learnt this in Boy Scouts if you didn't learn it in primary school. Our grid system on our topo map is a series of grid squares. We measure those grid squares in terms of eastings. So they're the vertical lines measured left to right across the bottom of the map, and northings, the horizontal grid lines, measured from bottom to top. And you'll see on the slide, each of those has a number. And we divide the space between our lines into 10. So remember, these are 1,000-meter squares. So each of our tenths is 100 meters long. So we give a position we describe it by its 6-figure coordinates. So the two numbers that introduce the square we're in, and then the 10th of the square in terms of left to right, eastings first, and then bottom to top, northings second. So we've got a feature there at point A. That's not the big point A, that's the little point A, which is 240 in eastings and 380 in northings. So my A's and B's have slipped there, I apologize. They're much smaller squares as shown there. So eastings first, cross the river before you climb the tree. Eastings first, then northings. The map tells you how to do this. You don't need to memorize it tonight. The map tells you how to do it on the back to tell you how to, if you need to contact search and rescue, how to give an exact position using the grids system on your topo map. So all of that stuff's on the back. All of the symbols on a topo are printed on the back of the topo. So you don't need to memorize them the way you do with marine charts. It's all there for you. Now, here's Port Stephens. There's a topo on the left and a marine chart on the right showing the same area covered. Okay, so as Campbell said, we need both of those. So here's the topo. Plenty of detail on shore, roads, population centres, communication opportunities, where you can buy lunch, where you can get access to a telephone. Really helpful for your pullouts. All the terrain and access paths are there. You may see watercourses as well, creeks, streams, but there's nothing about what's happening under the water. So looking at that topo map, now those of you who know Port Stephens will know the answer to this, but is it going to be safe for us to paddle from point A to point B in a big easterly swell? Yeah, nah, is the answer. So when we look at that same area with the marine chart, we can see that that ridge of shallow water extending out into the entrance. If we happen to be on the ebb as well, webinar 3, we'll be talking about swell and tidal stream in opposition. It's really going to stand up on that bank. So we won't want to be there with an ebb stream setting us down into the breaking water. So we really do need both. The topo shows us everything above mean sea level. The marine chart shows us everything below sea level. And we've got to have both for safe navigation. So now we're going to concentrate a little bit on what do marine charts tell us? What are the kinds of things we need to understand a marine chart? So the first thing is chart datum. So this isn't horizontal datum. This isn't what we were talking about with WGS 84 and GDA and all that stuff. Chart datum on a marine chart is the level below which soundings are represented on your chart. So how much water is there in a location? There will be a charted depth measured below chart datum. So the hydrographer in Australia tends to use the lowest astronomical tide as the vertical datum. I'm sorry, as our chart datum. So it is a vertical datum. So it means that every depth we see on the chart, there is at least that much water there. So we do understand that the weather can affect tidal levels. So we might be at the lowest astronomical tide, and it may go lower still because of weather effects. But in general, 99% of the time, lowest astronomical tide is as low as it goes. So it means there's a guaranteed depth shown on the chart. You will have at least that much water. The datum for heights is not the same. So what happens to the water moving above lowest astronomical tide? I'll show you on a graph in a moment what the different levels are. But our datum for heights is how high the water normally gets, not only ever gets at highest astronomical tide. So it's the mean of our high water springs. So high water springs are our higher high waters. The average of those higher high waters is what we measure heights from. Clearances, though, are a different matter. So if we have a mast and we need to pass under a bridge or a span of wire, it will have a clearance. And the clearance height is based on highest astronomical tide. So the same philosophy. We have at least that much clearance, irrespective of the tide. So here's how all those things connect. You can see the red line across the diagram there is our chart datum. Charted depths are measured below that. The top of the water is the height of tide at the moment. So above our lowest astronomical tide, we've got the mean of our low water springs. So that's the average of our lowest lows. Mean low water neaps is our highest lows, the average of them. Mean high water neaps is the average of our lowest highs. Mean high water springs, the average of our highest highs. And that's what we measure. The focal plane of a lighthouse is measured from mean high water springs. Okay, so that's how those datums connect. You'll see all of that explained on your chart. So marine charts have a title block that's like the back of a topo map. All of the detail you need to understand where your marine chart is coming from is shown in the title block. So I pulled out one of my Whitsunday charts and took a snap and just highlighted some of the things that are there. The information on depths and heights is shown there, what the datums are. The buoyage system that's in use on this chart, remembering that the world, unable to agree on a single system, has two systems of lateral marks. And this tells you which one applies on this chart. The GPS position error, can I plot directly onto this from GPS, or do I need to apply an offset? Are there any local magnetic anomalies that will send my compass weird? Tidal information, what are the datums here? What does mean high water springs look like? And really most important of all, particularly if you're worried about underkeel clearances, so not so much in a kayak, but often if you're yachting in this area, how much confidence can I have in the accuracy of the chart based on the age of the survey and whether it's been checked or not? Right down in the bottom margin, just out of shot, sadly, the model must have moved while I was positioning the camera, is the correction status. Marine charts, unlike topos, are corrected. They're brought up to date so that the latest dangers can be shown there. Okay, and that's important. If you're going to use a marine chart, it needs to be up to date. And we can update them either by applying to get the corrections for our chart. We can do all that online now. You can get Notice to Mariners that will correct your chart, and you can make the corrections yourself. Or you can go to a chart agent and get the corrections, or go to the chart agent, and if you're a lazy person, buy a new chart that's corrected up to date. The chart agent will do that for you. I just mentioned that the hydrographer welcomes advice if you see something that's not on the chart. That could be a danger. So we raise what's called a hydrographic note to tell the hydrographer that something is not as charted. And there's a web form for that now on the hydrographer's website. So it's a quick and easy thing to do. If you've got your iPad and you're within range of a signal, you can get a hydrographic note away. We may well be the first people to see a buoy out of position, for example. And if that's a buoy that's used for serious navigation, then the hydrographer and the Port Authority will welcome that advice. So we can use a hydrographic note. If we're in a harbour, we can use, there'll be a telephone number on the buoy usually that we can ring to alert them to the fact that the buoy has moved. But if you do see something that you think would be of benefit for other mariners, raise a hydrographic note. Even if it's regarded as inconsequential by the hydrographer, you're not going to get beaten up about it. You'll be thanked for taking the trouble. And that's the place we go to get hydrographic notes. That's the kind of a website that we'd use with the hydrographer. We can dive in there and we can download the notice to mariners that affect our chart. Now, there's a whole lot of symbols on a chart that you learn what they mean by using the chart. There's a great fact sheet on the hydrographer's website. So if you just go in there and search for marine chart symbols, it will bring up this fact sheet, which is about 3 pages of a PDF you can download. It is fantastic. There is a whole book of chart symbols. You don't need that. This fact sheet is enough to let you navigate in places like this, in the Whitsunday Islands, with complete confidence that you'll know what you're seeing on the chart, what it's representing. So as I say, I'm not going to go through in detail what an undersea cable looks like, or a pilotage reporting point, or any of those things. They're all on the fact sheet. What I'm just going to cover are just a couple of things that are important that you should know by heart when you're navigating in these areas. Firstly, depths and heights. How are they represented on the chart? So there's our chart datum in the center of that diagram. There's a 15-meter sounding has been taken there, and you can see how that's reflected on the chart, that 15 figure. We've got a 5-meter contour line there that has been, if you like, tested by the hydrographer. It's not just joining depths that are around about 5 meters. We can use that 5-meter line as a line of position. It will have been tested and surveyed by the hydrographer. That's where the 5-meter depth, where it gets deeper beyond that. And that'll be colored blue on the chart. The blue's not showing on my monitor here, but there is a blue tint applied to the 5-meter line. I've got a rock dangerous to navigation there. That the cross with the dotted line around it is showing us a problem area there. And here I've got a drying rock. So everything above chart datum, below mean high water springs, is what's called the intertidal zone. So this area covers and uncovers. When next webinar, when we're starting to talk about natural features, I'll get a photograph of what mean high water springs looks like when you're looking at a point of land. You'll see a thing called the hydrographer's black line, which is the way marine life dies off at the top of the intertidal zone, and you'll actually see where heights are measured from when you look at the land. So everything between mean high water springs and chart datum is the intertidal zone that covers and uncovers. A drying height, how high this will come out of the water, is shown. So that's metric again. That's 1.2 meters. It's underlined to show it's a drying height, not a sounding. Okay, and we can see how the other features, there's the 2.1 meter spot height. That's, if you like, ground that is always dry, also known as land. So that's staying dry, spot height 2.1 meters, with a surrounding intertidal area of rock. That's how it's represented on the chart. And this stuff is important. The tidal stream information, this is what your topo doesn't have. A flood stream and an ebb stream and the maximum rate will be shown with a straight arrow. If it's got fletches, if it's got feathers on the end, it's the direction and strength of the flood stream. If there's no feathers, it's an ebb stream. Okay, so that's how we know which is which. Sometimes they'll quote a springs and a neaps rate. If they don't, then you can assume it's the maximum rate at springs. Okay, but sometimes you will see a tidal arrow with a springs rate and a neaps rate. An ocean current is shown as a wiggly line, not a straight line. So tidal stream information comes and goes with the tides. Ocean currents are consistent over a longer period. And rips and overfalls and eddies will be shown. I did a paddling trip in northern Vancouver Island a couple of years ago, where there is something like an 11-meter rise and fall of tide, and the ocean or the seabed contour goes from sort of 30 meters to 200 meters in about 20 meters. The overfalls and races there were really spectacular and marked on the chart, so you could anticipate them. Once the stream started to run, you knew where you were going to get your overfalls and your eddies. Some charts will give you more detailed tidal stream information with a tide diamond with a letter in the center of it marked on your chart, and then somewhere around the margins of your chart you'll get detailed hourly rates of strength and direction of the stream. So Port Stephens, you'll see these. Whitsunday Islands, you'll see these. This one, it's referred to high water Devonport, so that's probably a Bass Strait special, I would think, that tide diamond. So it'll be related to high water at a standard port nearby. It will quote a springs rate and a neaps rate, so you've got to do some interpolating depending on the range of the day. Where are we between springs and neaps? Now, I'm just going to go through this really quickly. The boys, this is explained in the fact sheet, so we don't need to go through this in too much detail. But what I am going to focus on are the cardinal marks shown on charts. So Sydney Harbour, you can see all of these, boys, isolated dangers, safe water marks, lateral, that is port and starboard, buoys, and cardinal marks. So cardinal marks were developed so there was a universal global system for warning of a hazard and where the safe water was around the hazard. So the cones point to the safe water. So 2 cones point upwards, that's a north cardinal, safe water is to the north. 2 cones point downwards, south cardinal. East and west, similarly. Now I remember east because it looks vaguely like an egg if you squint. And W for waste or west, like May West, that's the west mark. So that's where the safe water is. Now, when you're at a distance from these things, you can't see the top marks. But these buoys are painted in black and yellow bands, and the cones point to the black band. Okay, so if they're not covered in bird guano, you'll see the colors before you see the top mark, and you can shape your course for the safe water. Okay, so 2 cones point upwards, black over yellow. East is black, yellow, black. Okay, so that's a quick way to recognize which of the cardinal marks you're looking at by looking at the bands of color and remembering the cones point to the black. We've got a little more there on how lights are reflected, but again, you'll get all that in the fact sheet. So what we'd like to round up with this evening is a bit on understanding contour lines. So contour lines, they are measured above mean sea level. So that's the datum that topos use for measuring their contours above. And a contour line, as I'm sure we learned in the Boy Scouts, is a line joining areas of equal height, okay, above our map datum. So when you see contours close together, you are getting a steep slope. When contours are spaced well apart, we've got a gradual slope. So here are a couple of photos. We're down off southern Tasmania here with some of our colleagues from the New South Wales Sea Kayak Club. Have a look at that feature just ahead of the sail there. Okay, here's what that looks like on a topo map inside the blue circle. And that's where we are, bottom center in that first picture. So you can get a sense of the shape there. Let me go back to the image. You see it just looks like a thumb sticking up in the air. When we look at it on the topo, we can see it's actually quite a large feature, but we're looking at it end on. We can see how steep that is by how close the contours are. A bit later that day, we've paddled further along. That's the same feature, now above the left paddle blade. Okay, so same feature, but now we're looking at it from this direction. Once we start talking pilotage, we're going to be talking about this a lot. How do we look at the land and relate that to our chart or map? And we do that by understanding what the contours are showing. So we've got a quick exercise for you here. So there's our contour map top left. We can see we've got 2 peaks on our little island here. And these contour lines are lines of equal height, remember? I've got 3 viewing points for that feature. One is center right, one is center bottom, one is bottom left. And we've got 3 views, 1, 2, and 3. Have a look at that and see if you can figure out which view connects to which feature. Okay, we all understand the problem. We're looking at that island from 3 different directions. Based on those contours, which of those positions matches our view? So have a look at how those contour lines match up. How high is the lower of the 2 peaks? Is that likely to be visible from some directions and not others? So this exercise is in the folder that we've given you the link to, and we'll repeat the link shortly. So here's the answer. So feature 3, we can only see 1 peak because that's nearest to us, and that's obscuring the lower peak. View 1, we can see a small peak rising above the lower levels of our first peak, and view 2 is showing us the valley between the 2 peaks. And there's another exercise like this in the folders where we've got 5 contoured islands and 5 views, and we'd like you to connect the feature with the contours. So that's available as an A4 page in a Word document in the folder, and so that's something worth doing in your own time after we've completed the session tonight. We're about to run out of slides and be able to go into a quick discussion. I know this has been thrown at you at 1,000 miles an hour, but it is just a whole lot of detail there we needed to cover to give us that baseline understanding of what we're seeing with charts and maps, what's their basis, and so on. Those contour exercises are there for you in the folder. I haven't done any exercises on plotting latitudes and longitudes, on reading eastings and northings, but that's something it would be good to do in your own time, just to make sure you're comfortable with plotting a position by its latitude and longitude. And we normally do that with a pair of dividers and a plotter. When we get to the practical day, we'll show you that the tricks for maneuvering yourself around the chart to get that stuff done easily. Doing some conversions of kilometers to nautical miles would be another good exercise that you can do. We haven't prepared quiz sheets for you. We'll leave that to you. So we've got a couple more things to cover in terms of what's coming next and what to remember from this, but we've now got a spot now to to deal with any questions that have cropped up. I can't see any in the chat, but if anyone's got anything they'd like to raise, please sing out, and Campbell or I will be happy to answer the questions. Any questions? Campbell, is there anything I've left out?
Oh, probably. No. No, I've been trying hard to fault you, Russ, to think of something that I could chuck in there. I think the perfect scale for deck maps on a kayak is something that one can have lots of discussions about, depending how far you're going to paddle in a day. But that comes after the pilotage stuff, not now.
That's right. Yeah. I'll just pop the link to the Google Docs folder back in the chat line too. And if any other questions crop up with you on today's exercise or webinar 1, I've got an email address there that's a disposable one that you can flick emails to me, and I'll be happy to respond. Come on, there must be at least one.
I've got one that you might be able to answer for me. I know that the topo maps are becoming obsolete from print. So they're only available digital now, and you have to print them, which I've had a bit of trouble with because the scale is not the same after you print them. Do you know if marine maps, or marine charts, I should say, are going to end up that way as well?
No, I wouldn't think so, because it comes back to what's legitimately used for navigation. So the paper marine chart is still the authority. And the electronic chart, to the same standard, is ferociously expensive. I mean, marine charts aren't cheap, but compared to an authorized electronic charting system, they're chicken feed. So I think that's going to be the driver that keeps paper charts available, if only for yachts people and recreational mariners. By recreational, I mean they're not at sea to earn a living. They're out there to fish or to carry tourists or that kind of thing, not moving bulk carriers from point A to point B. So because those users still need reliable charting information and can't afford electronic charting systems, I think that's going to guarantee paper charts for some time to come. What I'd like to see, go back a step. Charts used to be like family heirlooms. They used to be printed on cardboard, so they could last an 18-month ocean voyage. Then we went to thin paper about 50 years ago, ideally so they could be printed more often and more cheaply, but the government kept the charge up pretty high. That could be the breakthrough, that the government decides it can sacrifice revenue on paper charts and make them more readily available. And as some chart agents do, laminate them for you. So you can get them paper, waterproof, and be able to use them for a couple of seasons without deterioration. Of course, the other thing that might happen is we get a breakthrough like we did with aviation, and we get an approved electronic charting system that you can carry with an iPad. That's also possible. I feel your pain with topo maps. I was preparing for this webinar, reading the printing instructions, and I thought, holy mackerel, who's going to do that? It's really daunting, and maybe that's because most people now who are trekking are using a GPS with a topo map set loaded up, and they're not using paper maps as much anymore, and demand has collapsed. What we found with the last webinar was that the group had information on some of this stuff. Anyone in the chat who knows a little more about the topo printing process, or any companies that are now selling printed versions? Anyone got anything?
The one that that I've been using is I've found the best so far is 6 maps, because with 6 maps you can print to scale, and you can put them in an A4 size. But if you want the full map, you have to glue them or tape them all together to be able to get the full map.
Right.
Other than that, if you just use a generic program, I've got another one called Australia Topo, which I used at work today. We did an orienteering event today with my work, and because it wasn't printed to scale, it was really, really hard to work out whether you've gone past your checkpoint or whether it was coming up or where it was altogether, because you just didn't have those measurements.
Yeah. Talk about compromises when we're going to a paper map. That's even harder if you don't have a reliable grid system on it. Makes it even more difficult. I mean, it is interesting. I got back into flying about 9 years ago, I guess, and was carrying a flight bag that just used to make one arm longer than the other. And in a surprisingly short time, the electronic flight bag in an iPad was authorized. In Australia, there are 6 companies that can now sell a system that you can have on your iPad, and it's legal to carry that. You've got to have a backup, but a second iPad counts as a backup in the airplane, which is great. It's just a much more sensible way to go. And of course, it's what commercial aviation has been doing for some years. Different story at sea, because you don't have that refresh cycle, every few hours that you do with an aircraft. So you must be able to be self-sustainable. Any other questions or comments? I'll ask the group what I asked Campbell. Have I forgotten anything? Anything we've left out? Well,
I guess, Russ, you'll find out when you get to the practical session and ask for a task to be done.
Yeah, when we do this with the Sea Kayak Club, we do spend a bit of time practicing plotting positions by latitude and longitude, reading off the coordinates by eastings and northings. So I really do encourage you, if you can get hold of a marine chart and a topo map, and practice some of that stuff. Measuring a bearing and a distance from one point to another, those kinds of things. Just get into the habit of chart work. It gets easier the more you do it, like most things, but you will feel a bit clumsy and slow when you first start it. So getting a bit of practice will get you ready for the 19th of November, as Campbell says, when we'll go and have a splash around somewhere. No more. Let me just bring up what I think are the takeaways from tonight. So we talked about the oblate spheroid. We talked about latitude and longitude on charts, and eastings and northings on maps. We talked about what we mean when we talk about large scale and small scale. So a large scale shows a lot about a little. Okay, large scale, small area of the Earth that we're covering. Small scale, we see a lot of the Earth, but not much detail. We talked about direction and distance on charts and maps, how we measure those things. Measuring distance on a map is easy because we've got kilometre squares. On a chart, we've got to use the latitude scale on a meridian or the scale bar on the bottom. So the only place on Earth where you can measure a minute of arc on a parallel of latitude, and it will be a mile, is at the equator. Everywhere else, a minute of longitude is less than a mile, until we reach the poles where it disappears, etc. So we measure our miles on the latitude scale down the meridian, so on the sides of our marine chart. But on a topo map, every grid square gives us a kilometre measure. We talked about the horizontal datums, WGS 84, GDA, Geocentric Datum Australia for maps, and why we need both marine charts and our topo maps. One tells us everything above the waterline, one tells us everything below the waterline, and we need both of those together. On a marine chart, remember your vertical datums, lowest astronomical tide is chart datum for depths below that. So you've always got that much water, whatever the height of tide. Mean high water springs for heights, and highest astronomical tide for clearances. You've always got that much clearance under the bridge, whatever the height of tide. Do have a look for that fact sheet on the hydrographer's website. It's really good. You can pop that onto your iPad and as you're reading to work on the bus, really useful. And think about contour lines, how we judge the shape of the land that we're looking at by the position of the contours. Together, the steeper the land. And coming up next, pardon me, our practical day on the 19th, 11th of October is the Natural Phenomena Day, winds, tides, currents and swells. And the final webinar, 8th of November, navigating from the cockpit. We are done. Unless there's any more from you guys. Let me just have a drink of water.
That was awesome, Russ. Thank you so much.
Diane,
A
you're
lot
most
of
welcome.
information.
Thanks for all the comments in the chat line, guys, too. That's very thankful.
No, it's
I'm
good.
very thankful for your appreciation. That was great. So yeah, the next one, we're well on the way of preparing that one. We'll have a few more exercises for you that will hopefully make the time speed by. Although the 90 minutes goes really fast in these things. I feel like I've only just started. But that one should be good. And the final one, navigating from the cockpit, that's where we'll give you a lot more come in handy mental arithmetic tricks. Adrian normally tries to embarrass me by making me quote reciprocals of a 3-figure bearing in 2 seconds or whatever I'm allowed. Growing up at sea, you just learn these tricks and you can do things quickly and hopefully reliably and accurately. So those are in our sessions to come. So no more. Oh, it's kind of disappointing. We'll have to sign off.
You must have done a great job, therefore.
Thanks to Campbell for coming along and helping out. Thanks, mate. They were useful interventions, and you're most welcome to come and join us in the subsequent sessions too, if you want. We've got a few kayak club people lurking in the shadows here, like Steve and Marty. So yeah, it's great to see you all. Well, I guess that's it, Diane. We have no more to cover. We're on time, which is embarrassingly awkward. And thanks again for the comments in the chat line, folks. That's great. Appreciated.
Thank you for all your time and effort. Much appreciated.
No problems.
Thank you, Russ.
We'll see you all on, well, those of you who wish to, on the 11th of October.
Yeah.
And do our next one. Thanks, guys.